So today we're going to be talking about the concept of gravitational potential energy. Or the potential energy associated with the force due to gravity, or just gravity itself. All right. So as we stipulated already and before, we already know that the total amount of work done on an object is equal to the change in kinetic energy of that object, which is equal to F net cosine theta delta x. But this is our general equation for work in terms of changing an object's kinetic energy. So if I have a box, I pull it a certain direction, I'm going to change it, let's say from rest to some final speed. So I'm changing its kinetic energy from 0 to some final kinetic energy. Because if I have, let's say, have my box here and I pull it to a certain, over a certain displacement to a new position, then I'm changing the object's kinetic energy. So here it was at rest, VI is equal to 0. And if I just, I'm in a state of pulling it at this point. So if I take a picture at this moment, it's going to be moving at some particular speed. VF is equal to something that's not 0. I have changed the object's kinetic energy from 0 in the beginning. The initial kinetic energy was 0, but then the final kinetic energy is not going to be 0 because at this moment I'm still pulling it, it's still moving, it still has a speed, and therefore I'm doing work on the object because I've changed its kinetic energy from nothing to something, right? It's gone from a one state to a new state. I've changed its kinetic energy by changing its speed. So again, net work is the change of kinetic energy. So let's say that I had a system that just consists of a ball and the earth. I have two objects and the ball is resting on the earth. So I'm going to close this system off to the outside environment, and I'm just going to have the earth here, and let's say I have a ball on the ground, just resting. So my system consists of ball in the earth. And so a system is generally, it's two or more objects. So in this case, ball on the ground and nothing's happening. So how much work is done by the earth on the ball? Anybody want to take a stab at that? So the ball is just resting. How much work does the earth do on the ball? Anybody want to take a guess at that? How much work is done?
Would it, because isn't gravity still acting on the ball? So it'd be like 9.8 or negative 9.8.
Remember the concept of work. You know, work involves a force and a displacement.
Okay.
So the ball is at rest. Therefore, how much work is done by the earth? Is there a displacement happening when an object's at rest?
No.
So, correct. So therefore, how much work is done by the earth on the ball?
No work.
No work at all, because it's not moving. Remember, work involves force and a displacement. So F net delta X. Even though, as you said, Miles, the force of gravity is there, correct, but there is no displacement, so therefore there's no work. So now there's zero work in this case. I'm going to raise the ball from the ground. So at the ground, let's say at this point, so I'm going to raise it up. So I'm going to go. I'm not looking at the x-axis now, so I'm going to be looking at the y-axis. So this initial position here, I'll call it 0. There is no displacement. There is no change of position. It's just 0 all the way through. Time is going. There's nothing happening. No work done by the force of gravity. So now let me raise the ball in the air. So I've changed the look of my system to this. So I have my Earth here. I've raised my ball. It's at this point now. My force due to gravity is going to be pointing down towards the Earth because gravity acts downward. And then my displacement, oops, is going up like that, delta y, because I'm raising it up. Okay, so now at this point, I have changed my position. This is my starting point, and my 0 point, y initial is equal to 0, to some new position that I call y final. And we know it's not 0. It's some place in the air. Now the ball is stationary, so I've lifted it up. It's now just at some position in the vertical axis. So the ball is at rest, it's stationary, and we have negative Fg and delta y. Now here's a question to you. The ball is in the air, it's at rest. How much work does the Earth do at this point? We have force due to gravity and we have a displacement. How much work does gravity do on the ball, the force of gravity do? Now remember, the ball is at rest. It's not moving. Does Earth do any work on the ball? Remember, in order to have work done, we have to have a force and a movement. It has to move over a displacement. If the ball is at rest, how much work does the Earth do?
Would it still be 0?
It would still be 0 because the ball is at rest. You have to have some sort of displacement. You have to have some sort of motion in order for a force to do some work. Even though both of these are present, there's a displacement up in the air and the force due to gravity going downward, but there is no motion because I'm just holding the ball in the air. Just imagine that you're just holding something. Those two those two vectors exist, the force due to gravity and delta y, but there is no motion. So therefore there is no work done. Okay, correct. Again, the work done by gravity equals 0. Because the ball is at rest. And moving forward, there is 0 work done by the Earth because of 2 reasons. There is no displacement. And since there is no displacement, since I'm not moving the ball, I'm just holding it, there is no change in speed. Therefore, there is no change in kinetic energy. It's just staying there in space. I'm holding it in the air. So since those things are both 0, no displacement delta y, no change in kinetic energy, there is no work being done by the force of gravity. So since there is no change in kinetic energy, it doesn't move. So I'll leave that a little bit. So just think about that as we move along. We're going to get to the point is coming in the next statement here. So I lift the ball up, the ball's on the ground. There's no displacement. We can kind of, know that there's no work being done there because there is no change of position. It's just at rest. There is no movement. I lift the ball in the air. At the moment or at that point where I have the ball in the air, there's still no work being done by gravity. Force of gravity is coming down. I've lifted it up to that point, but at that moment, I do not have any work being done because it's at rest. It's at rest on the ground, and it's at rest at that point in space. So what can we say here? We have force due to gravity. We have a vertical displacement. We have a height. So why is there no work done? Since there is no work done, what can we, is there something else that we can say? But since there is since there is a force due to gravity, remember Fg is the force due to gravity. Since there is an Fg and there is a delta y that is, technically I'll say this, vertical displacement, or it's simply put just a height, as a height above 0. And we know that delta y is final position minus initial position. In this case, my initial position was equal to what? Anybody else? Ian, y initial was equal to what again? The ball was on the ground, so y initial was equal to? Or anyone else want to chime in? Alex, Mark. Initial position.
Zero.
I'm sorry?
0.
Y initial was equal to 0. The ball was on the ground. So that, I mean, if we were just trying to find the vertical displacement, we know y final will be some number and y initial will be 0. Okay, but delta y is a height or vertical displacement. Since these two vectors exist, the force due to gravity, and there's a delta y, we can say that there is the potential. It is possible to move that ball. So I'm holding it up in the air, and at that moment, the force due to gravity has the potential to change the position of that object. If I let it go, gravity is going to move it down. The force due to gravity is going to be placed down, moving in a downward direction, and the height is going to also be pointing downward as well. So the force due to gravity does have the potential to change its kinetic energy. It has the potential to change its position if I let it go. But at that moment, the energy at that moment is what we call potential energy. So I'm going to be more descriptive for that right here. So since those two vectors exist, there is the potential to change the kinetic energy. It's not changed yet, but it is possible, or the potential to do it. We call that potential to change the kinetic energy. We call the potential to change that kinetic energy the potential energy. Or better yet, since we're talking about the force of gravity doing work on this object to move it downward, specifically this potential energy is referred to as the gravitational potential energy. Simply put, we have the work done by gravity, which is equal to change in kinetic energy. So any force can change its kinetic energy. That force, or that work done by gravity, can also be associated with the change of potential energy. In other words, at that moment, the object stopped moving, but it has the potential to move. It has the potential to change the kinetic energy. So since we...
Mr. Kelly?
Yes, sir.
Can you go up a little bit?
Yes. Let me know.
A little down. Right there.
Okay. Ball is in the air, nothing happening. I have the potential to do something. And we call that potential, we call that potential the potential energy. Okay, I'll move. All right, so specifically put, so at this moment, ball is at rest. So I have the ball in the air. If it's at rest, then this doesn't exist. There's no motion because kinetic energy is the energy of moving things, energy of motion. So what I do have is just this change in potential energy, which is going to be final potential energy minus initial potential energy. And this potential energy is going to be equal to the force due to gravity. Let me see. It's going to be equal to the force due to gravity times the vertical height, delta y. Now, force due to gravity is mg from first principles. Mg is the force due to gravity, and delta y is going to be y final minus y initial, change in the vertical height. We stated that the initial position, the initial height is equal to 0. So this just becomes mg y final minus 0 because y initial is 0 there. So whatever y final is, it doesn't matter. We know that it's going to be something other than 0. So we say mg y final. So at this moment, the work done by gravity is equal to mg y final. Now again, work involves a displacement, a change of 2 points, a change of position. We have to go from one position to another position. In this equation, or in this formula here, we only have one position. So at the moment, I still have the ball in the air. It's just resting at y final. So I'm not going to be using the term the work due to gravity anymore, because the work due to some force, the work due to gravity, the work due to by tension, the work done by friction is always going to be a difference between two positions. So instead of calling this equation work done by gravity equals mgy final, we call this equation here just the potential energy. Because at that moment, I have the potential to do something. I'm not doing anything yet, but I have the potential to. And once I let the ball go, now I'm changing my position from that point to the ground. And that is where we put in the work due to gravity, change in kinetic energy, change of position. But at that moment, it's just potential. Nothing happens. Like somebody tells you, you have great potential, but you're not doing anything with it. You're just going to be where you're going to be, right? So same thing goes with the ball here. It has the potential to do something. It's not activated yet unless I drop it. And so that energy is what we call potential energy. And since it's at just one point, we don't have to bother with saying y final or y anything. It's just at that point, y. So we just say potential energy is mg y. But since, normally we associate y with the height, so we can just say, we don't have to say mgy, we can say mgh, just to be consistent with our text. So this is our formula for potential energy, and specifically gravitational potential energy, because it's the potential energy associated with the force of gravity. So better yet, we can just say PEG is equal to mgh. And this is our formula for gravitational potential energy. And that's where that comes from. So Any questions? Anybody need something else written before we go to an example? So I'm looking at the ebook here. And get some examples. All right, so I'm at page 85 of the ebook. And that's specifically page 254. And I'm looking at these practice problems. Additional practice at the bottom of 254, page 85. So in this example, we want to find the potential energy of this system relative to the ground. I'm just gonna, when the book is on the shelf, right? And so I'll give you a chance to do this in 10 to 15 minutes of breakout rooms, just to ponder this. Find the potential energy of the book Earth system relative to the ground when the book is on the shelf. Second one would be, I'm going to write everything out, but find PE of the book Earth system relative to ground when book is on the desk. And so this phrase here, relative to ground, this is always your starting point. This is your baseline. Hence, when we go back to the original question, it said relative to desk and shelf, because so you're looking at desk shelf system, or the difference between desk and shelf. Now, these two new examples here, relative to ground, we're looking at just the ground all the way up to the shelf. In part B, it's going to be ground all the way to the desk. And then the last example. Okay, I'll give you a chance to make sure you have those. So first thing, okay, we got the potential energy in an example there, and the problem. So now we're going to find the potential energy of the book Earth system relative to the ground when the book is on the shelf. Okay, we're going to go all the way from ground to the shelf. In part B, find the potential energy relative to ground when book is on the desk. And then find potential energy relative to shelf when book is placed back on desk. Okay, those phrases, relative to, that's your starting point. That's why when we said relative to desk, okay, we don't look at anything else. Desk is starting point. Okay, now I got to go up to the shelf. What's the height difference? Boom, potential energy, mgh, done. And that's the logic that you're going to do for these examples. Does everybody have this written? Ready to go? What is the height going to be?
It would be 2.1.
That's right, 2.10, 2.1. Yeah, because we're looking, we're starting from the ground, going all the way up to there. Started from the bottom, now we're here. All right. 2.10. So let's do that. You guys know that song? Okay. Gravitational potential. Yeah. Started from the bottom, now we're here. Okay, gravitational potential energy, 2.2 kilograms. 9.8 gravity. Height is 2.10. Thank you, Miles. That's right. We're starting from the ground, going up. And we do that, and that's just calculated. 2.2, 9.8, 2.1. 45.2 or 45.3 joules. All right, but ran out of space. Okay, so the second question, find the potential energy relative to the ground when book is on desk, and then all right, so desk, we're gonna go from the ground, which is our 0, 0, and the desk is gonna be 0.8. So that should be fairly easy. We wanna find the potential energy at this point, but you know, in this case, the change in height is gonna be the actual so-called height from between final minus initial. So the height is going to be 0.8. Because next time we want to get into the true dynamics of between potential energy and change of potential energy. We kind of are doing it here. So gravitational potential energy is mgh, where h is going to be 0.8. Basically, because we're looking at the potential energy relative to the ground when book is on desk, and so the height is just going to be 0.8 meters. So let's see, that's going to be 2.2, 9.8, and 0.8 meters. So that is 9.8. It's 0.8. That's going to be 17.25. And the last question was maybe a little tricky. Find the potential energy of that system when the book comes down from the shelf back to the desk. So now we change our point of view. We're going to go from the initial, now we're coming from shelf down to desk. We're going down, we're dropping in potential, which we'll get into next time. So H initial, that's going to be the position is going to be 2.1, and this position is going to be 0.8. So the potential energy is going to have a so-called negative height, or we're just going down, all right? So we're changing the position from the top to the desk there. H final minus H initial, that becomes 2.2 times 9.8, and then 0.8 minus 2.1, which is negative 1.3. Something interesting about this result is that it's the negative of the first example of the actual problem. And that's going to be negative 28. Yeah, negative 28.03. The negative 28, the first one was being 28 joules. And so something to be said about here is that gravity is going to do work in bringing that book down from the shelf back to the desk. So when gravity does positive work, we are going to be losing potential energy. It's going to be a negative result, as we can see in this result there, that number. But again, we won't get into the fullness of that. This is, takes us a little bit off topic for our context, but you'll see that the potential energy, the amount of potential energy does not change between the same two positions. So in the first problem, we went from 0.8 to 2.1. In this example, we're going from 2.1 to 0.8. The amount doesn't change. It's just, are we gaining position? Are we gaining potential energy as we do in the actual problem, or are we losing it? In this case, we're losing potential energy. And as we lose potential energy, the work done by gravity will be positive. Why is that? Because gravity points down, and this particular example, the height points downward. So they're both in the same direction. So the work is going to be positive. The work done by gravity is positive, but the potential energy in this case is negative. Okay, so more of that next time. Take off for the day. See you Friday. Homework due tomorrow. And that's it.
Bye, Mr. Kelly.
See you later.
Bye, Mr. Kelly.
Have
Bye,
a good
Kelly.
Mr. Kelly.
Have a good one.
Mr.
And the
Kelly.
notes are going to be due at 12:30. I'll put the slide up.
Thank you, Mr. Kelly.
You're welcome.
Mr. Kelly,
Yes, sir.
when did you say was the due date?
The what?
The notes, the due date.
Today at 12:30.
Okay.
Yeah.
Have a good day.
YouTube.
Mr. Kelly,
Yeah. What's up?
can you go to boxes part where it was right under gravitational potential energy?
You mean the notes?
Yeah. Right, now go up.
Okay,
Keep going.
that's it.
Oh, that's it?
Because I don't think well, that was just the example. But everything started at this point.
Okay, thank you.
Mr. Kelly,
Yes.
can you go to A? I didn't get A.
Oh, okay. The example there.
It was at the end, yeah.
This guy. Okay.
Yeah. No, the answer.
Yeah, so that is 45.3. Because we're going all the way from the ground up to the shelf.
Mm-hmm. Thank
So,
you.
Yes.
Bye, Mr. Kelly. Have a good day.
Bye, Jorge. All right, see you. Anybody else? What's up? So Anthony, Miriam. All right. You guys good? All right, that's it.